So I find today's lecture to kind of be a little bit odd in that we moved to the movement of rigid bodies. That's kind of the phase we're at in the course. And we're doing kinetics of rigid bodies. And today we're basically, it almost feels like we're taking a step backwards because we're going to be looking at pure translation of rigid bodies. And there's one big idea that really drives why we want to go back and look at this particular thing where we're looking at pure translation of rigid bodies. It is the idea that there are times when it is useful to be able to sum moments around some other point for a body besides the point that is the center of gravity. Okay? Sometimes it's way more convenient, I'll say, to be able to sum moments about some other point other than the center of gravity. And you might remember that with their basic equations of kinetics that I have written up here, it was important for us when we were doing especially this, sum of moments equation right here, we had to sum moments around the center of gravity, and we had to use a moment of inertia also about the center of gravity. Well, what's interesting about today's lecture is we are actually, by going to a pure translation, it makes that second or that last equation there, the moment equation, makes to where we're not using it. And yet, when you sum those moments and set them equal to 0, if you decide to sum about some other point other than the center of gravity, it actually will mess you up unless you take something into consideration that we're going to look at today. And that thing is called a kinetic moment. And so that's what this little development is that I'm about to do right here, is to come up with this extra term that allows us to consider this thing called a kinetic moment. In your book, the kinetic moment is denoted with this little sort of script-looking M sub k. And so they have a little bit different procedure of going about describing this thing to you than I'm going to show you. But what I'm going to do, I'm calling this a semi-general development. I'm doing this for a problem for which there are very few numbers or anything, but it gives you an idea of what exactly you're doing when you take into consideration this thing called a kinetic moment. All right, and this is the problem right here that I'm going to do this for. Imagine you have some general shape like this, and that general shape has these pins that are allowed to slide in these slots, okay? And by having these two parallel slots with two pins, that will constrain motion for this body to where it will be purely translational. Would you agree with that? So that body is not rotating now. It is purely sliding because those two pins are constraining it as such, okay? In addition to like weight, mass, and that kind of stuff, we also have an additional force of F that's applied at some angle of theta. And I actually put it on there so that the line of action of F would pass through point A. The reason I chose this as a scenario to kind of illustrate the power or why you might want to use this is that by having that force go through A, it starts to become really attractive when we look at this setup to think about A as a point around which to sum moments. Remember, by choosing a point, whenever you're summing moments, if you can get a large number of your forces that have lines of action through a particular point, that can help simplify your equations significantly, right? So I look at that and I go, wow, that'd be really nice if I could take a problem like that and sum moments about point A. And so that's what I'd like to do here is set that up, and I'm going to do this kind of two different ways. The first way I'm going to do it is the way that we know works, okay? The way that we know works is with the set of equations that I have up there at the top, right? Those are the equations that I know are going to work for this body. So let me go ahead and look at this free body diagram, okay? The free body diagram, to kind of complete that free body diagram, those pins, if those are frictionless slots, then those pins will each have a capacity to have a force acting normal to the pin. And so I might call this FA. And we could have another one up here that I might call FB. Okay. And I sort of already filled in a lot of the rest of the detail. I may have lost my, my little theta there. I'll add that back on. Okay. But that's, you know, mostly what you would need to do if you were going to do a free body diagram is imagine for the constraints, what would those reactions look like? All right. As far as the kinetic diagram, what do you think I need to know on the kinetic diagram? Okay, I probably need to put on here how the thing is accelerating, right? Because under these influences, there's no way that I can be sure that it's going to be static, right? So I need to account for the idea that it can accelerate, and if it accelerates, it will accelerate such that the center of gravity there moves or accelerates in the direction of the slots, okay? And so I may call that A sub g for the acceleration of the center of gravity. All right, so there's, you know, didn't have to add much, but that's how I got my free body diagram and my kinetic diagram. Once I have these diagrams, I'm ready to write equations. Okay, so which equation do you think you might like to write first? All right, I'll tell you what, let's just kind of go in order of, let's just do x, y, and then moments, okay? So we'll just first sum moments here, or sum, excuse me, forces in the x. Okay, in the x direction, what forces do I have that have x components there? Okay, yeah, F times the cosine of theta. All right, that's it. That's the only force, x component force that I've got, right? And so that's going to be equal to what? Well, it's a dynamic problem, right? And so this is going to be equal to the acceleration of the center of gravity of this body, which is the same as the acceleration anywhere in the body, given that it's purely translating, okay? So I'll just go ahead and say this is going to be equal to the mass of the body times the acceleration that I named A sub g right there. All right. Good deal. What about the y direction? Okay, in the y direction, I'll have FA plus FB, okay, plus F times the sine of theta. All right. Anything else in the vertical direction as far as forces? That's a good point. I never did put on here the weight, but I can do that, right? Maybe I'll just put, you can put mg if you want, or you can just put weight. I'll put mg. Okay. So I might subtract off of here mg. And then what? Okay. Yeah, so we could put mass times acceleration, but the acceleration in this direction is just 0 because of how it's constrained. It can only move left and right. It has no capacity to change in velocity in the vertical direction because of how it's constrained. And so we just put 0. All right. So far, so good. Now what? Well, now we want to do a sum of moments. And like I said a second ago, we're going to start by just doing it how we're used to doing it, right? We'll sum moments about the center of gravity. Okay, so for summing moments about the center of gravity, what all do we have here for these moments? Okay, well, first of all, maybe I'll start with FA. FA gets multiplied by what? WA. FB, positive or negative? Negative FB times WB. Okay. What about my weight? Does it create a moment around the center of gravity? No? Okay. So I can leave that one alone because it doesn't create a moment around the center of gravity. What else? Okay. So I need to deal with my F term that I have down here. Okay. So that would create a positive F times the cosine of theta times what? HF. Okay. What else? Anything else? No? Okay. That's fine. We don't need to have any other forces on there. But what do we set this equal to? Zero. Why is it zero? Okay. The reason it's zero is that it has these two pins and they're both constrained to go perfectly horizontally, right? It means that there cannot be any change of angle of the body, right? So how it's constrained keeps there from there being any angular acceleration for this body. All right, so that's good enough for now. Let's do a couple of things here. The first thing I want to do is go in here and solve this equation for F. So F is going to be equal to m times a sub g over the cosine of theta. All right, so far so good. Why do you think I'm doing that? I'll tell you what, before I go too much further here, let me write these equations a second time, but instead think about centering it around point A rather than point G. Okay? So first of all, do the x and y equations change? No. So those two equations stay exactly the same. So, I could set up these same equations with this other orientation where we're looking at around point A instead of around point G. The only thing that changes now is my moment equation. And what does the moment equation look like? Okay. Well, what I have in this case is I'm going to have FB times what? WB plus WA, right? And is it going to be clockwise or counterclockwise? Clockwise. So I'll say minus FB times WA plus WB. Okay. What about my FY? I'm sorry, not FY. What about my weight? MG, right? MG would be a positive mg times WA. All right, what else? Well, one thing we know is that it's still not accelerating angularly, right? So over here, I can just say this is going to be equal to 0. But one of the things that bothers me then about this is that these two sets of equations cannot both be true, right? Like it's unlikely that both of these equations are true. So there's probably going to need to be something that I add into this second set that is more suspect because it's not applying the rules that I said right at the beginning where I'm summing moments around G. I'm probably missing something that I need to add back into this equation right here. But one of the things I'll say then is that FA has been eliminated from that moment equation, right? So what I'm going to try to do is rearrange my original equation up here so that I eliminate FA. Okay? So what if I try to solve this for FA? I have FA is going to be equal to minus FB, okay, minus F times the sine of theta plus mg. Like this. All right. And what I'm going to do now is I want to basically go in here and start replacing some things. So the first thing I want to do is go and replace this F here. All right, so let me give myself a little bit of room. This equation right here becomes FA is equal to minus FB minus m a sub g over cosine of theta times the sine of theta plus mg. Okay, and I want to replace that same f down here in this moment equation. So down here, let me actually do two things. I'm going to replace everywhere that I have FA, I'm going to replace it with this whole expression right here. So I have minus FA, oh, not minus FA, minus FB, minus MAG, okay, and actually what is sine over cosine? Okay, tangent, so MAG tangent of theta, okay, plus mg. All this gets multiplied by WA. All right. Next, I'm not trying to eliminate FB, so I just leave that alone. I have minus FB WB. But the next one I want to do a replacement of is this F that I have right here. And so here I've got MAG over the cosine of theta, okay, times the cosine of theta. Times what? Times HF is equal to 0. Okay? All right. So there's a few things we can do here. One of the things we can do is we can eliminate that cosine that I have right there. Okay? So that divides out. What else can I do? Can I distribute some things? So, like for instance, could I take FB and imagine, you know, sort of collecting that FB, right? So I have minus FB times WA plus WB. That'd be appropriate, right? To kind of collect those two together. Okay. The other one that I would have here is I might have a plus mg WA, right? And then I'm going to have this minus m ag tangent of theta. Okay, and I think that takes care of, now that I've handled all of those, I think that takes care of everything up to this last term, which is just going to be m ag hf. All right, which is pretty good, but there's actually a little bit further we can go on this. And I think I maybe missed one more term. This was MAG tangent theta times WA. All right, so I missed a term right here. Let me just sneak that WA right in here. Okay. All right, so all this is going to be equal to 0. What I was about to say is we can do a little bit better than this because there's a little bit of geometry that we happen to know. Okay? We happen to know that this is HF, even though I may not have written it on there. That's HF right there, correct? And there's a little triangle that gets formed right here that may be useful to us. So there's a little triangle that gets formed right there. So let me actually, pull that triangle out, draw it a little bit bigger. Okay. That triangle right there, we know some things about it. For one thing, we know that the base of it is WA. Would you agree with that? Because that's, if this WA is measured from this line, kind of the y-axis right there, over to A, that's how far that is. The other thing that we know is that over here, this height is HF minus HA. Okay? And the last thing that we know that could be useful to us is that this angle right here is theta. Okay, we know that because those are just basically two intersecting lines, and this was theta over here, so that must be theta over there. So what is the tangent of theta? The tangent of theta is always, for a right triangle, opposite over adjacent, right? So the tangent of theta is equal to HF minus HA over WA. Well, that's kind of interesting, and that might actually help us out down here, because I could actually take this one further and say WA times the tangent of theta is equal to HF minus HA. And that allows me to do a substitution here for WA tangent of theta, right? So this becomes minus FB times WA plus WB plus MG WA minus M AG, and now I'm going to do my substitution here, HF minus HA plus M A sub G HF. Well, now that's kind of interesting, because this term right here cancels this term. Okay, you see that? That I have a negative one of those terms and have a positive of the same term. So those two things cancel out. And so this ends up leaving me with minus FB times WA plus WB plus MG WA. Okay. And here we're going to have plus M AG HA equals 0. And here's where that really starts to become interesting. Look at what I had down here. Right? When I was summing moments around A rather than summing moments around the center of gravity, I had most of that. Right? Everything's the same except what? MAGHA. Right? That's an extra term that showed up, or actually, technically, it's a term that went away by me summing around a different point other than the center of gravity. Okay? And for the one that I'm sure of, I know that this one up here, the one in green, I know that this one is right, because that's what we came up with originally, was that you sum moments around the center of gravity, and that is going to be proportional. That's so summing moments around the center of gravity is something that I know is right, and it better be the same as if I sum moments around point A. And so this gives rise to the reasoning as to why we have to add another term if we're going to sum around a different point other than the center of gravity. What is typical to do is to actually take that term, which this term, that little term right there, this is what's known as the kinetic moment. Okay? The kinetic moment is found by multiplying mass times the acceleration of the center of gravity times HA is the distance from that center of gravity. It's the perpendicular distance from the vector that describes the acceleration to the point that you are summing moments around rather than the center of gravity. Does that make sense? That's what HA is, right? That's this little distance right here, right, is HA. So you take that distance from the line that describes the acceleration to the point that you are summing moments around, multiply that by the mass times the acceleration, and that gives you this kinetic moment term, right? What I was about to say is what's customary is to actually include this kinetic moment term instead of showing it on the left side of the equation. It's customary to show it on the right side of the equation, which if I do that, this ends up being a minus M AGHA. Let me show you why it is that this is how it's done. Okay? What you can do is you can go back to your kinetic diagram and you can look at the acceleration of the center of gravity and imagine it, even though it isn't actually a force, you can think of it as a force. That acceleration times mass, you can visualize that as a force. And on the kinetic diagram, it has a, if you look at this particular one that we're working on here, it would have a clockwise orientation, right? It would create a clockwise moment around point A if AG was a force, right? So what you do is you pretend like all of those accelerations that you might have on your kinetic diagram, you pretend like those are forces, and you add up the moments that those would create around the point that you're summing moments around, and you put it on the right side of the expression. Okay? That's exactly what we did here. Right? We had a counterclockwise. That M times A sub G is kind of like a force, and you multiply that by the length HA, and that gives you this kinetic moment term. Okay? So that's, again, that's this part right out here. This is your kinetic moment. So just to kind of summarize there, if there's some real good reason for the problem that you're trying to work, if there's some real good reason why you don't want to sum moments around the center of gravity, that's okay. But when you do that, you have to be careful and remember to put in this kinetic moment term to compensate for it. Okay? Physically, a good physical example of this is, what if you have a book that you're trying to slide across the top of your, the surface of your desk or something. What you'll notice is that if all of a sudden you just pushed really hard on the bottom of your book, what would happen? Right? The book begins to topple. Right? The reason it begins to topple is the fact that the book does not want to accelerate basically resists motion, and it becomes like a force that pushes back this way, and it creates a moment. Right? That is an example of, if you were to sum moments, for instance, around the base of the book, which would be a very attractive thing because all of your friction terms or other forces, they all center down there at the bottom. So it's a convenient place to sum moments around. It just doesn't happen to be at the center of gravity of the book. So you can actually still sum moments around the base. You just have to also include this kinetic moment term, which basically acts like another force, even though it's happening due to the fact that it doesn't want to accelerate. Okay? All right. This is the background that I wanted to do. Now I want to work a problem. Sound good? So we're going to work a problem involving two dissimilar material balls sliding down an inclined plane.